Hello, I'm Shaumik, and I'll be presenting our work, StRegA, Unsupervised Anomaly Detection in Brain MRIs using compact context-encoding variational autoencoder. I have no financial interest to declare. Deep learning-based techniques are widely used in several research fields, including medical image analysis. Most of them use supervised learning, which requires a manually annotated training dataset. Creating such a dataset is really time-consuming. Moreover, it is also difficult to represent the vast array of possible anomalies for a given organ in a given training dataset. An unsupervised anomaly detection system can be a possible candidate to address these issues. Variational autoencoder-based techniques have been proposed for the same, which attempt to learn the distribution of the anomaly-free dataset without any annotation, but many of them perform poorly while detecting pathologies in clinical data. This research proposes StRegA, an unsupervised anomaly detection pipeline that attempts to improve a VAE-based model's performance by simplifying its output. We focused on anomaly detection in brain MRIs. The StRegA pipeline can be divided into three parts: pre-processing, the main model, and post-processing. Pre-processing includes brain extraction followed by segmentation, both using FSL. Then the data is standardized. Then during training, data augmentation techniques are also applied. Finally, the 3D volumes are split into 2D slices and interpolated into 256x256 matrix before supplying them to the model. As we are working with a simplified form of the input, we proposed a compact version of the context-encoding VAE model, or CCE-VAE. The post-processing is only applied during inference. The model's output is first subtracted from model's input to generate the initial mask. Then the negative values are removed, and it is thresholded using Otsu's method. Finally, morphological opening is applied on this to remove noise, and then it is interpolated back to the original size as the input. These 2D masks are stacked together to obtain the final anomaly mask in 3D. The model was trained on anomaly-free brain MRIs by calculating the total loss, which was a combination of Kullback-Leibler divergence and the reconstruction loss using L1 loss, which was then optimized using the Adam optimizer with a learning rate of 0.0001 for 60 epochs. During training, the model attempts to learn the mean and standard deviation of the Gaussian distribution of the healthy dataset. For training, mood and ICSI datasets were used, while for testing, three different datasets were used: mood toy dataset, artificially creating an anomalous dataset using the mood dataset, and finally it was tested on a clinical dataset, the BraTS brain tumor dataset. The performance of the method was compared using the DICE score on those three test datasets against three baseline models: SkipAE, GMVAE, and ceVAE. Additionally, a baseline was created by combining the StRegA pre-processing steps with the ceVAE model. Two sets of training were performed by combining the mood dataset with T1 and T2 weighted ICSI datasets. They were then tested on BraTS T1 and T2 weighted datasets respectively. It can be seen that in both cases, the proposed StRegA pipeline outperformed all the baselines. Furthermore, it can be said that the pre-processing steps had a significant contribution to the success of StRegA, indicated by the results of ceVAE combined with the StRegA pre-processing. A final observation from these results is that the performance of all the models were better on T2 weighted dataset. Now let's have a look at the qualitative results. Here are 4 example slices from BraTS T1 weighted dataset. The columns from left to right are the input image after the StRegA pre-processing, reconstruction by the CCE-VAE module, thresholded difference image after StRegA post-processing, and finally the ground truth. It can be seen the method was able to detect the tumor except for the really small scenario. The next examples are from the BraTS T2 weighted dataset. It can be seen that the performance is better, agreeing with the quantitative results, but here also we can see some undersegmentations. Now let's have some comparative examples. The first row shows an example from the artificially created anomalous dataset, and the second one from the BraTS T2 weighted dataset. It can be seen that StRegA performed considerably better than the other models, which is in agreement with the quantitative results. We further extended the pipeline as an assistive technology where the segmentations were converted into lesion detection. We can see that in every example, both T1 and T2 weighted BraTS MRIs, the method was able to detect the location of the tumor. So now to conclude, we have proposed the StRegA pipeline and the compact ceVAE module here, which achieved significant improvements over the baselines. securing average dice scores of 64% and 86% respectively, while segmenting tumors and artificial anomalies. Under-segmentations were observed in every scenario, but the method could localize the tumors properly. Finally, this was extended as an assistive technology. In the future, we will be evaluating the performance of this approach on other types of anomalies, and techniques other than segmentation will also be assessed to simplify the input. The code of this research is available on GitHub. Thank you so much for your attention, and feel free to contact me for any questions or feedback.